Have you ever encountered a problem that initially seems impossible to solve? Maybe this has happened in a chemistry or a physics course. What do you do? Hopefully, you don't throw your hands up in the air and walk away, because that's not very professional. As a budding engineer, you're going to be asked to solve many problems that may at first seem impossible. To solve these problems, you need to take an inventory of what you know, simplify the system you're analyzing, make some assumptions, and then apply the appropriate models. You hopefully already have some practice taking an inventory of what you know from some physics or chemistry courses. In this video, I'm going to review the concept of simplifying a seemingly complex system in order to solve a problem. First, let's talk about systems. Systems are all around us. The exact definition of a system is going to depend on the person you're talking to. For engineers, we consider a system a volume that contains matter we want to study. This is quite a broad definition. You can use the word system to describe a number of things, including global systems, like those related to climate change, systems that are geographically defined, like a watershed, a continent, a lake, or even something like a business, a device, or a reactor. I went for a walk and collected some images of some systems around us. This puddle is a relatively simple system we can look at. Whenever you consider a system, think about the system boundary. For a puddle, it's not so clear. Maybe you want to define the boundary as the edge of the puddle and only consider the water within the puddle. Maybe you also want to consider the mud or the dirt at the bottom of the puddle, 1 inch deep, 2 inches deep. In all cases, you should choose a boundary relative to the problem you're trying to answer. Different problems, even on the same system, may have different system boundaries. This puddle could be an example of a closed system. A closed system is where no matter is going to be flowing past the system boundary. We don't have flowing water into or out of our system. It's just an isolated puddle. There may still be interesting things happening within the puddle. Maybe microbes are breaking down compounds, maybe some algae is growing. We would want to consider these reactions, chemical, biological transformations of matter within our system. These changes don't require any mass to flow across the system boundaries. In another example on the same system, what if we wanted to consider evaporation? What if we wanted to think about how the size of our puddle is changing with time? When it rains, maybe there's some water infiltration from the ground or into the ground, or evaporation. Well, then we would need to call our puddle an open system because we're considering the water flow across the system boundary. The assumptions you make about your system, for example, if it's an open or a closed system, will depend on the question you're trying to answer and the relevant timescales. If we're looking at some microbial reactions that happen over a course of minutes, then maybe we just assume that our puddle is a closed system. However, if we want to look at the size of the puddle changing over the course of a year, then we call it an open system. Therefore, the system boundary, and if you consider if it's open-closed, is going to depend on the problem you're trying to solve. In general, you should make your model system as simple as possible when you're addressing a particular problem. Sometimes you might start working on a problem and learn that your model system is too simple or too complex. If that happens, you can always go back, redefine your system, and start again. This is a tree, obviously, a very complex biological system. Trees and plants provide several ecosystem services that environmental engineers might be interested in. This could include, depending on the species, uptake of metals in mine sites. This is called phytoremediation. Vegetation also takes up nutrients, stabilizes slopes to protect against erosion, slows rainfall runoff, and contributes to evapotranspiration. From a global perspective, trees take up carbon dioxide and produce oxygen, and increasing forest cover could help slow the buildup of carbon dioxide in the environment. We can think of this tree as a system. The boundary can include all of the tree's biomass, maybe even the part under the ground, the roots. Maybe we want to include symbiotic fungi in the soil. Would you consider a tree open or closed as a system? Depending on the problem, maybe you want to consider the tree an open system and look at the uptake of roots, through the roots of water and nutrients across that system boundary. Here we see Butte. While the puddle and the tree were natural systems, Butte is an engineered system, a system conceived of and built by humans. You can look at the town and see one great system with several subsystems. Where would the system boundary be? Is it open or closed? As you think about these things, you think about the potential problems you need to solve. For example, how does the number of people in Butte change with time? If we were considering that problem, we might consider the boundary of the city limits. We could collect census data to set a population density cutoff for what we would consider the town of Butte. Or we could eyeball it, just draw a boundary. If we were looking at how the number of people in town changes with time, we could consider the flow of people in and out of the town via the highway systems or the airport. These flows are something we could estimate, or maybe we need to be very exact, maybe we need to measure them. All these flows will tell us something about the changes in the number of people in Butte over time. They will not tell you the population of Butte. So for that, you'd need to look up a census or make an estimation. We can also think about the many subsystems in Butte. We can think about water delivery, the sewage system, the public transportation systems, power systems. All of these systems are very important for the function of the town, and they're really important systems for many of the engineers that work in Butte. Here's an image of the Berkeley Pit. This is a defining feature in the Butte landscape. It was an old copper mine. It's about 1 mile long, a half-mile wide. The mine was first dug in the 1950s, and miners progressively dug deeper and deeper over time until the mine closed in the 1980s. While miners are digging open pit mines like this one, they pump the groundwater to lower the water table. When an open pit mine closes, these pumps are turned off and the groundwater starts rising again. This slow refilling of a pit presents a real challenge. The oxygenated water reacts with rocks and produces sulfuric acid. Therefore, the water in these pit lakes is normally quite acidic. While the Berkeley Pit water used to be about a pH of 3, it's now closer to 4, and the pH is slowly rising, perhaps due to some ongoing human activities. We can consider the Berkeley Pit system. Drawing a boundary for this system may be difficult. What do you want to consider? Do you only consider the water in the pit? What about the rock surface? The Berkeley Pit connects to many of the old underground mines below Butte. Do you consider those? Is the Berkeley Pit a natural or an engineered system? Maybe it's a combination of the two. You would choose a system boundary that would help you answer the questions about the Berkeley Pit that you have. Let's consider the water level of the pit. This is an important question because the pit is now a groundwater sink in the area. Therefore, all of the contaminated groundwater underneath Butte flows towards the pit. If the water level rises too high in the pit, then the direction of groundwater flow would reverse, and contaminated groundwater would start flowing away from the pit and potentially cause a regional groundwater issue. The pit water level at which this groundwater flow reversal would happen is called the critical level. If we were interested in modeling the Berkeley Pit water level, we could draw the boundary along the edge of the Berkeley Pit. We could consider inputs and outputs of groundwater, like We could consider water inputs and outputs, like contributions of groundwater and evaporation. There are also some surface water inputs, and there are ongoing mining operations that affect the pit water level. We can quantify or estimate these inputs and outputs over time, consider the geometry of the pit, and model the water level over time and into the future. Finally, let's look at this stream. Streams, rivers, and lakes are very commonly considered environmental engineering systems. Maybe we're interested in the contribution of snowmelt to the volumetric flow rate of this stream. Think about these things. Where would you draw the system boundary? Is the stream open or closed? This brings us to the end of our introduction of systems. Here are a few things to remember. First, a system is a volume that contains matter of interest. It may have an obvious boundary, like some sort of chemical reactor, but it may have an ambiguous boundary. You, as the engineer, get to decide the boundary suitable for your problem and realize that this boundary may change depending on the problem you're trying to solve. And there are some instances where you could even choose multiple boundaries in your system in order to solve a more complicated problem. Systems can be open or closed. In an open system, matter flows across the system boundary. No matter flows across the system boundary in closed systems. And finally, a system can be natural, like a tree, or an engineered system, like the city's sewage system. And some systems are a combination of both. Now, you should be able to move around in your daily life and identify a multitude of systems. Think about their boundaries. Think about if they're open or closed, are they engineered, natural, or a combination. Once you can do this, you can start simplifying even complex systems in your mind, a practice that will help you solve many engineering problems.